Welcome to the explainer that literally turns abstract linear algebra into your ultimate engineering toolkit. If you've ever stared at a massive equation and thought, okay, but how does this actually build a bridge? Well, you are in exactly the right place. Today, we're decoding the math of space and structure.
Let's ground this math in physical reality right off the bat, okay? Think about a suspension bridge. Every single force acting on it, the displacement of a beam under a heavy load, even the velocity of wind slamming into a skyscraper, these are all vectors. And I know the math can look super intimidating at first glance, but honestly, just two basic tools, length and angle, are the master keys to unlocking almost everything you need to know here. Master these two, and you master the forces. It's that simple.
Since you're gearing up for your Mathematics I exam, here is our quick roadmap for today's session. 1. Vectors in engineering. 2. The Euclidean norm. 3. The dot product. 4. Orthogonal vectors. 5. A step-by-step worked example. And finally, 6. A quick final exam recap.
All right, let's jump straight into section 1, vectors in engineering.
Let's look at the actual mathematical language you need to define the blueprint of literally any structure. In Rn, which, by the way, is really just math speak for n-dimensional space, a vector is a mathematical object made up of n real numbers, usually stacked vertically in what we call a column vector. Now, in pure math, sure, it's just a list of coordinates, x1 down to xn. But to an engineer, those numbers perfectly represent the distinct components of a physical quantity. They give you both the exact direction and the sheer magnitude of a force in space. Moving right along to section 2, the Euclidean norm. So we've got our vector, but how do we actually measure the physical length of this force? Well, that's where the Euclidean norm comes in. You just take each component of your vector, square it, add them all up, and take the square root. But here's the really cool part. This isn't just some random algebraic formula you have to blindly memorize. When you calculate this norm, you're computing the exact physical length of a steel beam or the true magnitude of a displacement force in the real world. Checking out the authentic lecture notes we have right here, you can see exactly where this formula comes from. It's actually just the Pythagorean theorem scaled up. See how the length, labeled L on the sketch, is just the hypotenuse of the right triangle formed by coordinates x1 and x2? Whether you're working in 2D space on your notepad or 3D space out on a construction site, this geometric truth holds up perfectly to give us that norm. All right, section 3, the dot product. We've completely conquered length, so let's shift to our second essential tool. This one is all about angles and measuring how different vectors align with each other. There are actually two ways to think about the dot product. Algebraically, it's super easy. You just multiply matching coordinates, like x1 times y1, x2 times y2, and then add them all up. But the real magic? That's in the geometric equation. The dot product is exactly equal to the norm of the first vector times the norm of the second vector multiplied by the cosine of the angle between them, which we call phi. This single equation mathematically reveals exactly how two interacting forces push or pull against each other. Viewing these professors' notes side by side absolutely nails it. It brilliantly illustrates our dual toolkit. On the left, we're measuring the sheer magnitude, the actual length, using our Euclidean norm. And then on the right, the notes walk right through the trigonometric reality of the dot product, locking in that geometric angle. Put them together, and length and angle tell you everything about how forces interact in any structural system. Which brings us to section 4, orthogonal vectors. That natural connection between dot products and angles leads us right into a massive high-yield concept for your exam. Think about this. What happens to our dot product formula if the angle between two vectors is exactly 90 degrees? Well, the cosine of 90 degrees is 0, so the entire dot product just becomes 0. This is the absolute golden rule you need to memorize. Two non-zero vectors are completely independent, meaning they're geometrically perpendicular or orthogonal if and only if their dot product is exactly 0. Okay, section 5, a step-by-step worked example. Grasping the theory is great and all, but applying it while the clock is ticking during a math exam, totally different story. Let's walk through a classic exam-style problem straight out of your university exercise sheets. We've got a two-part challenge today. First, we normalize the vectors, and second, we find the exact angle between two resulting vector sums. First up, normalization. As detailed in the lecture notes here, to normalize any vector, you just multiply it by the scalar fraction of 1 over its Euclidean norm. By dividing a vector by its own length, you're basically stripping away its magnitude.
What you're left with is a pure directional vector with an exact length of 1. It points in the exact same direction as before, but now it's fundamentally standardized.
So let's put it all together for the actual problem. Step 1, calculate the norms of your two vectors using Pythagoras. Let's say you get the square root of 10 for the first one and the square root of 90 for the second. Step 2, divide the vectors by those exact norms to normalize them into pure directions. Step 3, multiply their matching coordinates to find the dot product, which in this specific exercise works out to negative 0.6. And finally, step 4, because the dot product equals the cosine of the angle for normalized vectors, you just take the inverse cosine, or arccos of negative 0.6. That pops out an exact angle of roughly 127 degrees. Boom, full marks on the exam.
Finally, Section 6, our final exam recap. We've covered the physical meaning behind the math, we've nailed the exact calculations for length and angle, and we just crushed a full example. Now let's lock it all in. I highly recommend taking a mental screenshot of these essential formulas right now. Seriously, these are your 5 undisputed foundational rules: the Euclidean norm for calculating geometric length, the normalization formula to scale vectors down to a length of 1, the algebraic and geometric dot product equations, and of course the orthogonality rule, where the dot product equals 0. As you head back to your studying, always remember the real-world engineering reality behind these numbers. Resolving any complex physical force into safe, manageable components always comes down to mastering just these 2 simple concepts: length and angle. So I'll leave you with this to ponder. If the structural integrity of a massive suspension bridge ultimately relies on identifying orthogonal forces, where a simple dot product equals 0, what other absolute physical truths are hiding in plain sight within the math you're learning today? Keep exploring, keep questioning, and hey, good luck on that exam.